Dear students and the participants on the course on railway engineering, in today's lecture we will completing our discussion on the transition curves and then we will move to the next item, that is extra clearances. If you remember, in the previous lecture we started with a negative cant which is provided on the branch line, and we did some numericals so as to calculate that negative cant and the cant on the main line, and finally the speed which can be provided on the main line. Then after that we started a discussion on the transition curves, wherein first of all we talked about the purpose and then what are the various requirements, and then finally we discussed about the various types of transition curves which can be provided, and out of which few which have been used by Indian Railways. And at the end we have talked about the computation of the length of the transition curve on the basis of three criteria. In today's lecture we will continue with our discussion. We will do some of the numericals so as to understand the concepts, and then we will move to the laying of a transition curve. Then we will discuss about the two types of the curves, the compound curves and the reverse curves. And once we have completed with the transition curve, we will move to the next topic, that is extra clearances. Let us look at the first numerical here. The data which is being given is, it is a broad gauge which defines that G is 1.676 meters, it is a group A route. The curve is 1 degrees, maximum permissible speed is 100 kilometers per hour, actual cant is 135 mm. We have to calculate the length of the transition curve. So, rate of change of the cant in the desirable value is 35 mm per second, and for that the length is being given by this formula, that is L is equals to 0.008 into Ca into Vm. So, if we put the values here where the Ca is being given as 135 mm and the speed is also being given as 100 kilometers per hour. So, those two values have been put here, and what we get is 108 meter as the length of the transition curve, so as to satisfy this condition. As an extension of this particular numerical, it may happen that these values, their maximum permissible speed and the actual cant, they are not being given, and you have to calculate these values, and then once these being calculated can be input here so as to calculate the length of the transition curve. Now, another criteria is the rate of change of the cant deficiency. So, here again this is the formula is same, only Ca is being replaced by Cd, and cant deficiency in the case of a group A route we are taking as 100 mm. So, it is 100 mm multiplied by the speed, what we get is 80 meters. So, if you have to satisfy the cant deficiency, the change in cant deficiency, then in that case the lower length is sufficient. The third criteria was on the basis of the cant gradient, where we talked about that it can be 0.72 Ca or it can be 0.36 Ca at the minimum level. So, this is a desirable value which needs to be provided. So, if we use this, it is 0.72 into Ca is 135. So, we get 97.2 meters. That means, if 97 meters are being provided, then it will be satisfying the cant gradient. Now, we have got three values 108, 80 and 97. So, whatever is the higher we are considering that. So, we consider 108 as the length which can be provided. So, if we consider this 108 as a length, we can recalculate the gradient, and we will find that the gradient is already being satisfied because we were requiring only 97 meters here. Now, let us move to the next numerical here. It is a Rajdhani route. The curve is 1 degrees, maximum sanctioned speed is given as 130 kilometers per hour, actual cant is 50 mm, transition length is 60 meters. The length of the transition curve cannot be increased due to the proximity to a yard. Calculate the maximum permissible speed on the track. So, as the curvature is being given, the radius can be calculated by 1750 divided by d, that is the formula. So, what we get is 1750 meters. Now, safe speed, the formula is 0.27 into under root of Ca plus Cd into R. So, considering that formula, Now, CA, CD and R is calculated already here as 1750, actual cant is given as 50 mm. So, we has 50 mm here and CD can be taken as 100 mm. So, considering these values, the speed which we get as a safe speed is 138 kilometers per hour. Now, let us look at the transition length. So, we are being given that transition length is 60 meters. Now, if we consider that transition length, then the length was being defined as what? There were three formulas which were given, and within those, in the case of a cant or a cant change, rate of change of cant or cant efficiencies, we have the desirable condition and the minimum condition which has to be there. So, based on those, considering the 55 mm per second as the rate, the formula becomes V is equal to 198 L divided by Ca. So, when we talk about L, that at that time we were calculating it. So, it was L is equals to V divided by 198 Ca into Ca. So, using this we get the speed here as 237.6 kilometers per hour. If we use the rate of change of cant deficiency, again not exceeding 65 mm. So, deficiency we are talking as 100, taking the length as 60 meters and using the same formula, what we get is 118.8 kilometers per hour. Now, if we check the cant gradient for a distance of 60 meters which is being given to us and the cant which is given as 50 mm, what we get is 1 in 1200. So, it is a okay condition because it is more flatter as compared to 1 in 720. Now, maximum permissible speed, we have got different speeds here 118.8, 237.6 and 138.3 kilometers per hour. These are the three values which we have got. So, out of these three values, the lower of the three, that is 118.3 kilometers per hour, can be taken up here. Now, we are making a check here that equilibrium cant is equals to actual cant plus cant deficiency. Now, equilibrium cant can be found out by a formula GV square divided by 127 R. Actual cant is given as 50 and for cant deficiency we have a formula as 198 into L divided by V, where L is the length of the transition curve. So, using this, when we put all of the values, the only variable which we are considering here is the speed V, and we are interested to calculate this value. So, we get an equation here. So, if we solve this equation which we have got, we get a value of V as 133 kilometers per hour, and this value of 133 kilometers per hour, this is more than the sanctioned speed. So, the sanctioned speed was given as 130 kilometers per hour. So, you cannot go beyond this. So, we have to restrict the speed to 130 kilometers per hour. Now, for this 130 kilometers per hour, if we calculate the cant deficiency using the same formula which we have used so far, what we get is 91.4 mm, and this is less than the 100 mm which we have considered on this Rajdhani route where the higher speeds are allowed. So, the condition is being satisfied. So, in that means in one case when we are talking about the transition condition, in the case of transition condition we got a value of 118.3 kilometers per hour, but when we are talking about the overall condition, then the speed has come out to be 130 kilometers per hour. So, there are two values now which we have. On the case of main section it can be 130 kilometers per hour, but in the case of transition section it will be 118 kilometers per hour. But you can see that in this case, as the things have got adjusted, there is not much variation between the two speeds, that is the speed on the straight track and on the transition track. Now, let us have a look on another numerical. This is again a broad gauge section. The radius is already given to us, not the degree of curvature. The limited transition length is 40 meters, maximum sanctioned speed is 100 kilometers per hour. Now, here when we are considering the length of the transition curve which is being restricted to 40 kilometers per hour, whereas if we talk about this 100 kilometers per hour as the maximum sanctioned speed, and if we try to calculate with respect to that the length of the transition curve, it would have become it would have come more. So, here the Kent has to be such that the speed on the circular curve is equal to the speed on the transition curve. So, that is the case which we will try to satisfy because of this restriction. So, that and so as to make that, we discussed that we have to adjust the Kents. So, the most favorable conditions which can give you the speeds on the circular curve or the straight sections and this transition curves is that if you go with a CA equals to CD. So, if we consider this and we consider the maximum rate of change of Kant as 55 mm per second, the maximum speed on the transition curve can be calculated. So, it comes out to be V is equals to 198 into L divided by CA. In the case of safe speed, it is calculated by 0.27 into CA plus CD into R under root of that value. So, we said that CA is equals to CD is an optimal condition which needs to be used. So, if we use that condition here, so it becomes CA plus CA and it is being equated with the previous condition. So, both of the values have been equated now, and when we equate this both of values, what we get is CA equals to 89.5 or 90 mm. Now, considering the Kent efficiency of 75 mm for a normal track, so we get the maximum speed as 90 plus 75 into 600 under root of that multiplied by 0.27, and this comes out to be 85 kilometers per hour. Therefore, the maximum permissible speed will be 85 kilometers per hour, and the maximum super elevation which we are providing here is basically 90 mm. Now, let us talk about the laying of a transition curve. So, we will be discussing the diagram which is being given on the right hand side actually. Now, first of all we have to calculate the length of the transition curve. So, this length of the transition curve we can calculate on the basis of 3 criteria. So, once we have got that, say this is the point from where the curvature is starting. So, here on this side it is a straight section and this is a point of tangency. So, there is a length of transition curve which is coming say up to this point. Now, this particular length, this is divided into equal parts, and previously also we did talk about it, and there also we said that it is better that if we take usually 8 equal parts. And then when we have taken those 8 equal parts, it means now you have got these particular points as 1, 2, 3, 4, 5, 6, 7, 8. We use the equation y is equals to x cube divided by 6 RL. So, we have the radius, we have the length of the transition curve, we have the x distance which we are moving, and for that x distance the offset y is going to be calculated. So, now this y is equals to x cube divided by 6 RL, this can also be converted into the form of a shift s. The shift s is L square divided by 24 R. So, if I put the values here, say x is equals to L. So, it will becomes L cube divided by 6 RL, or this will be L square divided by 6 R, whereas L square divided by 24 R is the shift. So, we can say that this is related with the shift in the form that 4 times of the shift if we take, then this value will come. So, there is a possibility that whole of this formula for the different lengths can be converted into the equivalence of shift. Say if we are talking x is equals to L by 2. So, if we put this x is equals to L by 2 in this equation, what we get is in the form of equivalence of shift as it is s by 2. So, when x is equals to L by 2, we have s by 2. So, that is this ordinate we are talking here. When it was L, so it was a total shift, that means this is the point where the circular curve will start. And if this circular curve is taken forward, it is being extended, it would have come to this value where this distance is L by 2, and at this particular L by 2, this transition curve, this is having a distance shift s here or s by 2 or s by 2 here. So, total shift is s with respect to the transition, and the transition curve when it passes through it, it is at a half of that. So, start of the transition curve is located by shifting the existing tangent point backwards by a distance equal to half of the length of the transition curve and shifting by s perpendicularly. So, we have shifted back and then we have gone by s. So, we have got this value L by 2 here and then we are getting this shift. Then offsets are measured perpendicularly to the tangent to get the profile of the transition curve. So, whatever y values which we are calculating, we are going to use perpendicularly to the main line. Now, one another type of curve is a compound curve. Now, in the case of a compound curve, if you see here on the diagram, there is a curve with a radius r1, there is another curve with a radius r2. The curvature is going in the same direction. So, when the curvature is in the same direction and there are two curves which are meeting each other, but having different radius, then this type of an arrangement is defined as a compound curve. Now, in this case, when these are meeting at this point, there may be a possibility that at this point that one curve is coming here and then there is a transition and then there can be another curve. So, this can be the case. So, here it is R1 and here it is R2, but in between it is transition. So, there is a possibility that we have a common transition in between. Now, for traversing the transition curve at a uniform speed, the length would be given by L is equals to 0.008 into CA1 minus CA2. So, there is a Kent which we are talking for the curve 1. So, here it will be CA1 and on the other side it will be CA2. So, it is CA1 minus CA2 into V. Similarly, if we are talking in terms of the Kent deficiency, it will be CD1 minus CD2 into V multiplied with a factor 0.008. So, whichever is greater is going to be considered as a length which is to be provided here in between as a common transition for the two curves. In the case of a reverse curve, what happens? In the case of reverse curve at a point of tangency, when you move outwards from that particular point, there are two curves which are meeting at this point, but they have a reverse curvature. So, this one curvature is in this direction, whereas another curvature is in the other direction, and they have different radius being provided here, may or may not be different, can also be equal. So, in this case again there is a possibility of providing a common transition curve, and the length of this common transition curve will also be governed by the same concept that we are calculating it for one and the other, but in this case the CA1 and CA2 which were in the previous case of a compound curve, they were subtracting out, here they are adding out. So, CA1 plus CA2 into V into 0.008 or CD1 plus CD2 into Vm into 0.008, whichever is greater is the value which can be considered in these type of curves. Now, for high speed groove AB routes, the minimum straight length of 50 meters should be provided on the broad gauge between the two reverse curves. If the straight length is less than 50 meters, then transition curve shall be extended in the shorter lengths, means that if that straight section is not there, see we are talking about a straight section and then we are working with these lengths. So, if this straight section is having a length less than 50 meters, then it is better to increase the length of the transition curves and meet them here. In this case, the rate of change of Kent and the Versine will be same along the two transitions. If the length cannot be increased over 50 meters or the straight line between the curves cannot be eliminated, then the speeds have to be restricted here to 130 kilometers per hour. Now, let us shift to extra clearances on the curves. Now, when we are talking about this extra clearances, we are moving on a circular curve. The bogie is moving at the top of it. So, the size of the bogie will be bit like this. So, there is a movement in the lateral direction, there will be a movement in the upward direction. So, bouncing can also be there can be pitching, all those things will happen, and due to which, as well as because of the super elevation which is being provided, there is going to be a shift of this bogy in terms of the squeeze which may happens. So, there are different things which will be happening here, and for that particular reason there is a requirement of providing some clearances here. So, there is an effect of the curvature, there is effect of the leaning due to the super elevation, there is a sway of the vehicles inside, and then there can be certain specific conditions like between the adjacent and the curved tracks. If the two tracks are being provided, so this is one track and then there is another track provided here. So, there is some leaning, some sway or some effect of curvature, because of which some clearance is required, but on this side then the total clearance which was otherwise taken up is going to be reduced. We have to take care of these aspects. The adjacent tracks with the structures in between. So, if there is something being provided here in between, then with respect to that also, and in the case of the platforms, we will look at all of these cases one by one. So, effect of curvature. Now, effect of curvature, as you can see here, A, B is the frame which can be there, but now what happens is because of the turning on the curve and because of the rigidity of the frame, the vehicle is not being able to negotiate the front at the back in the same form as the curve is being provided. So, there is nothing like following the path, and when this is not happening, then what will happen is that there is two conditions which are going to be created. One is an overthrow condition, another is an underthrow condition. It says that it causes the projection of the vehicle outwards, inner side of the curve at its central point and towards the outside of the curve near its end. So, it is going outside of the curve near its end, and on the inner side there is a projection backside. So, there is an overthrow and there is an underthrow which is happening. So, extra clearance is required, which is the distance by which the longitudinal axis of the body of vehicle moves out from the central line of the track. So, this is the central line of the track. With respect to that, it is moving out here. So, that is the value which needs to be considered. So, the extra clearance which is required at the center of the vehicle, which projects towards the inside of the curve, it is known as overthrow and is calculated by the formula c square divided by 8r. Whereas, in the case of the underthrow which is happening here, where the vehicle projects towards the outside of the curve, it is calculated as L square minus c square divided by r. So, whatever is the distance which is being left, so that is what we are considering here. So, we have one as overthrow, there is a one as underthrow. The overthrow, this is happening on inside and this one is happening on outside. So, we have to remember these things also. So, if you are calculating everything on the inside, and what are the things which will get added up, if you are talking about the outside, and what are the clearances which needs to be added. Now, L here was the length of the vehicle, C was the center to center distance between the bogies, and R was the radius of the curve. And this center to center distance between the bogies, which we have used in the case of virtual transitions, was around 14.785 meters. Now, effect of leaning due to super elevation. Now, if you see here, because of this super elevation being provided, there is a tendency for the vehicle to lean inside. So, this is the leaning, this is the extra amount by which the vehicle has gone inside, though it should have been up to this point. Now, what is happening? It is moving up to this. So, therefore, there is an extra value which is to be provided. So, it requires an extra clearance, and this extra clearance is defined by h into E divided by g, where h is the height of the vehicle, E is the cant and g is the gauge which is provided on the track. Now, if supervolution is not known, then the lean may be assumed to be 70 mm for 1 degree curve and 115 mm for the curves having degrees more than 1. So, these are the two values which can be considered subjective. The super elevation is not known. No extra clearance is required for leaning on the outside of the curve because it is basically shifting inner side. So, you can see here this is the shift to the inner side. So, it was supposed to be here, instead of that it has moved inside. So, there is no requirement of providing any clearance on the outer side. So, for outside we have only one value which was calculated previously as an and throw, and then we have an overthrow along with the leaning which is getting inside. So, this is an inside condition. Effect of sway of vehicles on account of the unbalanced centrifugal forces which are caused due to the Kent deficiency or Kent axis, the vehicle tends to experience the additional sway, and this acts on the inside of the curve and is being taken as 1/4 of the clearance due to leaning. So, in the case of the leaning, the value was h into E divided by g. So, 1/4 of this, that means h into E divided by 4g is what we are talking here. So, actual sway is going to be less than the required sway due to the centrifugal force, and it causes the bogies to remain towards inside of the curve. So, again it is happening towards the inside, it means in the third clearance which is coming towards the inside, whereas for the outside still we have one value. So, the total extra clearances which are required, say if we are talking about the inside of the curve because of overthrow, because of lean, because of sway, overthrow is c square divided by 8r, lean is E into h by g, and the sway was 1/4 of that, that is E into h divided by 4g. In terms of an outside, it was only and throw, and that is L square minus c square divided by r. This value of c from center to center distance, it is taken as 14,785 mm in the case of bogies being used on the broad gauge track. The length of the bogie is taken as 21340 mm for broad gauge, and height of the vehicle is taken as 3350 mm again for the broad gauge tracks. Now, the empirical formula which is being adopted in the field for determining the extra clearances required due to the curvature effect is, in the case of overthrow it is 27330 by r, in the case of and throw it is 29600 divided by r, and this value will be in mm. Now, another one is the extra clearance which is required between the adjacent and the curved tracks. Now, lean is not considered as both the tracks have the same super elevation. So, you have this track as well as this track. So, the same super elevation is being provided, therefore, whatever lean will happen here, the same lean will also be happening on the other side. So, the extra clearance here is the clearance on inside plus clearance on outside of the curve. So, what we have is EC minus lean plus and throw. So, EC1 which was the clearance on the inside was because of the overthrow, because of the lean, because of the sway. Sway was 1/4 of the lean, where now lean is being removed because in this particular case lean is not as an issue. So, the lean E into h divided by g, which was here as positive E into h divided by g, and then finally it becomes E into h divided by z. So, they cancels out, and what we are left is c square divided by 8r plus E into h by 4g plus the and throw, which is L square minus c square divided by 8r. Now, in the case of platform, what happens? So, in the case of platform, so if the curvature is like this and the platform is provided. So, platform is, though it is being given like a curvature, but still the gaps is probably is going to be more as compared to on the outer side. So, it is observed that the provision of extra clearance on the curves may lead to excessive gap between the footboard and the platform. So, footboard of the vehicle or the train or the coach and the platform, that gap is increasing. It is therefore stipulated to reduce the extra clearances by 51 mm on the inside of the curve and by 25 mm on outside of the curve. So, whatever total extra clearance which we have calculated, in the case of the tracks when they have the platforms on inside and outside, then we can reduce the values by 51 and 25. Let us look at the numerical here. The data is broad gauge, curve of 2 degrees, super elevation 100 mm, length of bogie is given, center to center distance of the bogies are given, height of the platform is given as 840. So, this length of the bogie is capital L, the center to center distance is capital C, this degree is there, super elevation E is being given, height of the platform is given here. Two high level platforms, one on inside and one on outside of the curve, calculate the required extra clearances for the platform. So, as the curve degree is being given, we convert it into the radius, and because it is 2 degrees, what we get is 875 meters. Now, the extra clearance on the inside of the curve is because of the overthrow, because of the lean and because of the sway. So, it is C square divided by 8R plus E into H by G plus E into H divided by 4G. So, when you put the values here, so C is 14785, R is calculated 875, E is given as 100, and then H is the height of the platform being given as 840. So, when we put all of these values, what we get is 42.88 mm, and we can round it off and it becomes 45 mm. Now, extra clearance which is required on outside of the curve, which is equivalent to the end through is L square minus C square divided by 8R. So, if we calculate this L square minus C square divided by 8R, what we get is 33.83. Now, as we discussed this criteria, that in the case of on the inside of the curve we can reduce it by 51 mm, and in the case of outside of the curve we can reduce it by 25 mm. So, we go back here. Now, this is the inside of the curve, we are providing 45 mm. So, if we reduce it by 51 mm, that means this will be a negative value, which is not at all possible, and that is the reason we have not reduced it by 51 mm, whatever the value is there has been used here. Whereas, in the other case, when you are talking about the outside, we are reducing it by 25 mm, because we have 33.83, we get 8.83, and that we round it off to 10 mm, the next value. So, the 10 mm is the clearance which can be provided in this case. So, with this we close our discussion now. We talked about the various numericals related to the transition curve length and finding the permissible speeds on the tracks. We also talked about how the transition curves can be laid in the field. Then two specific cases, one related to compound curves and one related with the reverse curves was taken up. And then finally, we talked about the various extra clearances which are required to be provided on the tracks or near the platforms in terms of end throws, in terms of overthrows, or leaning or sways or clearances at the platforms. With this we close this discussion. Thank you. We will be meeting in the next lecture.